Hello, everybody. My name is Siddharth Desai, and I'm going to be talking to you about a black box approach to sim-to-real transfer from the Austin Villa robot soccer team from the University of Texas at Austin. I mainly do SPL stuff, but this research is just broad machine learning stuff. And this is joint work with Haresh, Karnan, Ishan, Durugkar, Josiah Hanna, Garrett Warnell, and Peter Stone. So let's get started. The first thing is I just want to define the sim-to-real problem. We're talking about sim-to-real as it pertains to control tasks like walking and kicking. And in these sorts of complex behaviors, we would really like to use some machine learning tools to have the robots learn these behaviors on their own. But training in the real world can obviously be very expensive. It can be time consuming, and it can be potentially unsafe for the robot or for the operators in some cases. And so ideally, we would like to train in simulation. If you're unfamiliar with some of the other leagues, this photo here is from the 3D Simulation League, and this photo is from the SPL League. And so they're both, the 3D Simulation League is based off of this now robot. And so what happens if we try to train in simulation? Well, on the left, you can see a policy that was optimized in simulation. And you can see that it doesn't look very realistic. And indeed, if you just try to naively copy over that policy onto the real robot, it quickly falls over. Here's another view of that in slow motion. And you can see that the robot just quickly falls over its own feet. And part of the reason of that is just the simulation doesn't model the interaction between the soft carpet and the robot's foot very well. So in the real world, there's more, that interaction is more complicated, and the robot doesn't deal with that very well. So what sort of approaches are there to overcome this difference between the simulator and the real world? We call that the reality gap. And these are some ways that we might deal with that. One thing that a lot of people have tried is a robustness approach. This works pretty well in certain scenarios. And this is just where you train a policy that's capable of doing well in multiple different simulators, which just might be multiple parameters for the same simulator. Or this encompasses things like dynamics randomization, adding perturbations during training, this sort of thing. And in this method, there's sort of a trade-off between how well you want to generalize across domains and performance in any one particular domain. Another approach is this sort of bootstrapping approach where you do part of the training in simulation and then you finish the training in the real world. But if you have a case like we just saw in the 3D Simulation League, if your simulator agent is exploiting some inconsistency there, like the very uniform carpet, then you still have to unlearn that in the real world. So this may not actually be saving you that much time. And then the approach we want to focus on in this talk is the grounding approach. So this is where we use a little bit of real world data to make the simulator better, or to ground it. And our goal is to iteratively improve the simulator until we get the desired performance in the real world. I should mention that these techniques aren't like distinct classes. There are a lot of approaches that use a variety of these approaches or sort of fall in between. If you've heard of things like meta learning, then I would say that kind of falls in between these two categories. There's approaches that, use all sorts of different ideas from all of these different categories, but we want to focus on the grounding approach here. So in particular, we're using this paradigm called grounded simulation learning. And this entails doing some training and simulation, coming up with a good policy that works in your current simulator, then deploying that in the real world and seeing how it does, and using that data to then ground the simulator and improve it. And then you repeat by training in that grounded simulator, which should hopefully transfer better to the real world. And one loop of this procedure we call a grounding step. So one time around, one grounding of the simulator is a grounding step. And we'll use that terminology later on. So the key question here is, how do we ground the simulator? And one thing we might ask is, can we even modify the simulator? So if you've heard of system identification, that usually entails learning some parameters that you might not know about your simulator. But that may be difficult to do, to change those things, or your model in your simulator might not even be complex enough. Going back to the 3D simulation case, the model of the friction of the carpet is a very simplistic one, and it doesn't quite capture what we want it to capture. So that's in this talk, we want to focus on black box approaches, where we assume we can't modify the simulator, and can we still do some sort of sim to real transfer? So that brings us to this algorithm called grounded action transformation. So if you're not familiar with some of the reinforcement learning terminology, let me go over that. So we're dealing with a sequential decision-making process where you have an agent that's interacting with an environment. And so the agent produces an action, which is processed by the environment, and the environment produces a state and a reward, which the agent then observes. If you're coming from a controls background, instead of agent, think controller. Instead of environment, think plant. And the reward function is the negative cost function. So what we do to improve the simulator here is we add this block called an action transformer. And from the agent's perspective, everything else is going to be the environment. So the concatenation of these two blocks is going to be the grounded simulator. So let's break down what's going on in this action transformer. Over here, we have a forward dynamics model. So this is trained on the real world data that we're collecting from the robot. And based on those real world trajectories, we fit a neural network to say, what is the next state we expect to see given a state action pair. And this block is the inverse dynamics model, which comes from data we collect in the simulator. And that's asking what action takes us from one state to another. So when you put all that together, it transforms the action to something else, which hopefully will produce a state that's more realistic. If we've trained these networks well, then it'll produce a state that's more similar to what we would see in the real world. And this is sort of the crux of this algorithm. This little diagram might help explain that if that was a little confusing. So on the left, we have this simulator where these circles are the states. You start in S0, and you can take either A1 or A2. And if you take this top action, you'll get this reward of +1. If you take the bottom action, you'll get the reward of -1. So in the simulator, you'll want to take this top branch. But in the real world, the transition dynamics, which are these arrows, they're flipped. So in the real world, you want to take action A2. And so when we apply GAT, first we have this forward model. So you're seeing that this forward model mimics the transition dynamics of the real world. Then we get an inverse model, which comes from the transition dynamics of the simulator, except the arrows are actually going from the other way, from the states to the actions. And then you have the simulator itself. And when you kind of follow all these arrows, you'll see that in the grounded simulator, the best action is A2, which indeed matches the real world. So that's just a little toy example, but when we apply it to the Now robot, on the top you'll see a hand-coded walk. So this is optimized by a human that's decided on what the, just tried to find the best parameters by hand. And on the bottom, we have a set of parameters that's optimized using GAT. You'll see that the GAT one is clearly faster than the other robot. And at the time of writing this paper, this is the fastest walk ever achieved on these robots. Now I want to discuss some ongoing work that builds off of this idea. So recall this diagram again. One of the drawbacks here is that we have these two different neural networks that are feeding into each other. And that leads to some variance. It becomes a little hard to train in practice. And so ideally, we'd like to train this, this neural network as one block, one neural network rather than two separate ones. And the intuition behind this is sort of that if we assume that our simulator is mostly good, that in most cases we do get to the right state, then we only want to learn those small changes, the delta between the actions, rather than a completely new action. And so with two separate networks, it's very difficult to learn this delta, but with a single network, this becomes easier, actually. So how do we actually accomplish training this network? So remember that we're treating everything below this line as the environment. So everything here is frozen while the agent is learning how to walk or whatever action it's learning. So what we can do is we can treat the action transformer as an agent itself. And so now everything to the left of this line is the environment for this agent. And so the action transformer is trying to say, okay, what action should I take every time to make this transition seem more realistic? And the one advantage to doing it this way is that because we've now framed it as a sequential decision-making process, we have a reinforcement learning problem, and so we're now matching the whole trajectory instead of individual transitions. The way this agent knows what action is best is that we train the forward model as we were doing before, but rather than this forward model being a part of the action transformer, it simply provides the reward. So the forward model predicts a next state, which is given by this S tilde. And when the action transformer actually produces an action, the simulated environment is going to give a next state here. And so the difference between these two is the value that the action transformer is trying to minimize. So that's the difference between these is the negative cost, or sorry, the negative reward. It's the cost of this action transformer choosing this action. So here are some results from this new algorithm that we're calling RGAT, Reinforced Grounded Action Transformation. And here you can see this is a domain called hopper, and this little robot has to hop forward. So in the first grounding step, it does okay, but eventually it falls over. And then in subsequent grounding steps, it's doing much better. and it actually doesn't fall over until the episode ends. And then this is showing a comparison between this new RGAT approach, which is learning the action transformer end to end. This is the original GAT approach. And this is the naive approach where we're doing no grounding and we're just training in simulation and applying that to the real world. So yeah, these two fall over fairly quickly, and RGAT continues to go on. Oh, I should mention, in this case, when we say the real world, we're using a modified environment as a surrogate for the real world. So we have the normal Hopper domain, and for the quote unquote real domain, we're using one where the torso mass is increased by I think it's like a factor of 10 or something. It's a very large deviation, but it still manages to learn to ground the environment. This is another example that I think demonstrates the difference between GAT and RGAT really well. So in this scenario, we're doing this cart pull domain where, if you're not familiar with it, it's that classic problem of trying to balance a pencil on your hand. And the reason this works well for this example is because the action space is one-dimensional. So the robot can only choose to move right or left, positive or negative. And so you can plot all of the input actions versus the transformed actions here. And in this experiment, we're transferring from the simulator to itself. So this is the ideal scenario in which your simulator is perfect. You would ideally see no change in the transformed action. So everything should lie on this black line. But as you can see in GAT, there's a fair bit of variance. It tries to hug the line, but it doesn't quite do it. But in RGAT, since we are learning it as a single neural network, it manages to learn that quite well. This is another interesting result from the same domain. Here we are transferring from a simulator to a modified simulator. And on the left, you can see what happens when the real pendulum is heavier than simulation. You can see that the magnitude of the action sort of decreases because the pendulum is heavier, and so the same action is going to have a less magnified effect. And on the right, you can see what happens when we do the opposite, and qualitatively, you can see that the change is also opposite. So when the pendulum is lighter, then the same action is going to have a magnified effect. And another sort of orthogonal to that, we're looking at what happens when you try to do this black box simulation in a stochastic domain. So to create a stochastic domain, we made this sort of uneven terrain environment for the now. And it doesn't, this is trying to learn it with GAT, and it doesn't quite do a very good job because this environment is more noisy in a way. You can think of this as process noise, because every time the robot puts its foot down, the contact forces are slightly different, and it doesn't really know what they're going to be like. So the robot has a very tough time dealing with it, and it's really tough to ground this environment since it's so noisy. So going back to that toy example, we can sort of model this by here, we still have we have choice of 3 actions. In the simulator, the third action is the best. But in the real world, we have this going on. So what this means is if you take action 2, then there's an 80% chance that you'll go to S2 and a 20% chance that you'll go to S3. But S3 is just so much better that even if there's a 20% chance you'll go there, it's still the best action. So whereas here, the best action was A3, here the best action is A2. But when we apply this GAT approach, the first, the forward dynamics model just chooses the most probable action. And so you can't even actually get to this third state. And so if you train in this simulator, you'll say that A1 is the best action, which is different from both the simulator only and the real world only. So they all give you different answers in this case. So the fix to that is to use a distributional model for the stochastic transitions here. So for the forward model, if you use a distributional approach and model the stochastic transitions, then you can sample from that distribution when you actually train. And then you can see that these two, if you follow all the arrows, these two diagrams are the same. So when we apply this to the robot, we get pretty good results. The top row shows GAT in the first grounding step and the second grounding step, and it actually falls more consistently as the training goes on. Because somebody trying to ask a question? Okay. So yeah, here you can see GAT is falling over pretty consistently by the second grounding step. Meanwhile, SGAT learns to learn a faster walk, but it's not falling over nearly as much. And you can see kind of on the right is GAT, on the left is the stochastic GAT approach, and on the right you can see that all the robots fall over pretty quickly, and on the left they manage to get through, even though one falls at the end. So that was all I had. Thanks to all my collaborators. Haresh and Ishan are actually here, and they'll help answer some questions if you have any. Thanks. Okay, I'm seeing a question in the chat that's saying, are your actions joint positions? What are your states? Okay, yeah, that's a good question. So in here, we're assuming that for the algorithm's sake, we're assuming that you have a fully observable Markov decision process. So it's not a POM-DP, it's a MDP. But in practice, what we're using is I believe it was 4 frames of joint data. So it was, you can kind of use that to recover the velocity information. And for the actions, the actions are joint positions in this case. Although, the actions of the agent are the joint positions, but we're optimizing the things we were optimizing in this were the parameters for a walk engine. So there is like a little bit of abstraction there. Somebody else asks how the kinematic performance of the gyro accelerometer sensor is stable. So yeah, this actually wasn't something that we dealt with directly. This was handled by the walk engine, and like I said, we were just using this to optimize the parameters of the walk engine. But the way the walk engine handles this is that there's basically a direct. It doesn't actually do a lot of this fancy IMU integration stuff that the last talk was about. So what we actually do is we just use the sagittal and coronal rotations, like leaning forward and leaning to the side, and there's just a feedback loop that ties that in with the ankle's angle, the commanded angle of the ankle. So if it's leaning forward too much, then it just straightens out the ankle a little bit. And if it's leaning to the side, I think there's I think it does that with the ankle as well. It might be the hip. I don't remember off the top of my head, but yeah, it's basically a very simple proportional relationship there. The link can be where in the formula. I'm not sure what you're trying to ask. If you want to unmute yourself and just ask it, that would be fine. I'm scrolling through the participants, and I don't see any hands at the moment. Is the walk engine made in-house? We're actually using a walk engine that was developed by RunSwift, which is a different team, and they had at the time of writing this paper, they had like the best walk engine in the league, and so we just use that and saw can we improve upon the hand-tuned parameters by just using our grounded optimization procedure. There's a hand. Hide, if you want to ask your question.
Just a quick question. What kind of network did you use? Is it just a feed-forward network?
Yeah, it's just a feed-forward network for the GAT. It was just a feed-forward network. For SGAT, it's still a feed-forward network, except now we're learning a distribution. So we learn a mean and a standard deviation, and then we use a
like variational.
Yeah, it's that sort of thing where
Okay.
Yeah, but there's no like recursive neural networks or anything, no convolution or anything going on.
Also not sequential.
Yeah, no, none of that. Because we have the raw joint angles that we're using as a state. The vision is handled separately, so we do have like a convolutional neural network used for vision at some point, but in the SPL league, the processing power is, I think, much less than the humanoid league, so we end up doing a lot of like tricks like downsampling, converting everything to black and white. Some teams are doing that sort of thing. I'm not really the vision guy, but yeah, it's kind of handled separately.
Sid, can I jump in for a bit? I just wanted to say that it's a feed-forward network, and the way we kind of like get around the issue of like sequential decisions is by basically concatenating multiple states, like Sid mentioned earlier. And so just using a feed-forward network is enough.
I understand. That was it for me.
Mark asks, are you adapting the walk engine parameters for each step, or do you always use the same? We're using the same parameters in this case. We just learned the parameters once during the policy improvement. And yeah, I didn't actually discuss a lot about like the optimization procedure we were doing to actually learn the walk, because actually we used a variety of different techniques. In the NOW experiments, we were using CMAES for the optimization, but in RGAT we were using TRPO and TRPO and PPO at some point. So those are some RL algorithms that learn neural network for the control policy as well. And Jasper had a hand up.
Let me make sure that I understand that correctly. So basically the action that's coming out of your network is the parameters for the walking engine, or is it the walk command given to the walking engine?
So the network, let me get back to this diagram. So here, these actions that it's producing, this is actually coming out of the walk engine. So this AT is talking about the joint angles. And that's what we're doing the action transformer on.
Okay.
But the discussion with the, how we're actually implementing this, that sort of, when we go here, right now I've only talked about the grounding part. The actual training and simulation, hopefully our method is agnostic to that, and you could use any sort of training procedure that you want once you're given the grounded simulator.
And so maybe to also add on to that, your policy, the policy of the agent can basically be parameterized by any sort of parameters. And in this case, the parameters that we use to tune the agent's policy are the parameters of the walk engine. You can also imagine having, say, a neural network that predicts at each, basically predicts at each step what action to take. And instead over here, we're basically just figuring out what are the parameters of the walk engine.
Okay, thank you.
And as far as training data and training time, I think for each grounding step, we did 10 or 20 walks from this center point to, we had to walk from this to the penalty cross 20 times, and that was one grounding step. And then within 2 or 3 grounding steps, it converged to the right policy that was fast and everything. Yeah, we can probably share the presentation. I should mention some of the stuff is still under review. The RGAT and SGAT things are still under review, but we can, once they've made a decision on that, we can pass along the information to the committee, and they can, wherever they post this, they can probably add a link to that. You had a question?
Did you at some point consider differential physics engines?
For this work, we did not. If you're talking about if we were able to get like a derivative from this block, right? So this work is assuming we can't, and so I think if you could get a derivative out of this, then you could probably do something that trains this faster. But I mean, mainly the reason is because I don't think the SimSpark engine provides that derivative, and
it doesn't.
And also the things I think that we were mainly stuck on were the things that are like the contact forces, where you probably aren't going to get a good derivative anyway. You'll have like those hard nonlinearities there.
Okay, thank you.
Yeah, Alfie has a question.
How do you collect data and measure it for the real world?
Your connection was a little shoddy, but I think you asked, how do we collect the data for the network?
Yep.
Yeah, so when we're deploying the robot on the field, we just, at every frame, we just write the joint angles to a file, and then we just have those, they're written to a protobuffer, and then we copy them over, and that's just used for training the network in just a supervised learning sort of way. Does that answer your question?
Thanks.
Okay. Great. Arnie has a question.
Yes. Hello. Question is, the walk height looks really low. So this has been, I think, a common characteristic in the UT Austin walk in the last years. And the question is, how long with the optimized parameters can the robot walk before the typical effects of overheating joints start, like with the knee joints that they collapse?
Yeah, that's a good question and a good observation. For the people in the Humanoid League that are unfamiliar, the NOWs have this very common overheating problem, and the lowering the walk height sort of exacerbates this problem. So in practice, it does actually cause an issue, and so we can't use the fast walk all the time. And so we actually have it in our behavior to determine when is a good time to use the fast walk. And then we basically have the sprinting behavior. So we do try to limit when we use that. And we've tuned it such that like they can basically get through one standard SPL game before they need to rest. So one interesting observation there is when we did the SCAT experiments, to compensate for the bumpy carpet, it actually learned to reduce the walk height significantly. And that was just something it learned on its own. It was just an interesting quirk. Is there another hand? Oh no, those were hands from before. Okay. Haresh or Ishan, did you guys have anything to add that I missed?
No, I think you got everything.